And here are some of the folks who worked here at UT who I had the pleasure of working with over the years, and some visitors are back. So they're deciding. For example, Jay, we've been chatting together. There's postdocs that are joined the advice and stuff. So who cares? But the stuff that I care about science-wise, I was really trying to figure out how to link heat mantle dynamics with what's happening at the surface of terrestrial planets, mainly our Earth. And I've always had sort of this earthquake hobby, where on the left you see one of my favorite sort of foreshock aftershock sequences from Noto, and really trying to sort of bring these things together is what we're trying to do. So what I've been up to, sort of some introductory words, and some of my own research is for, I don't know, 5 years or so, starting with the postdoc Lucas Fuchs here, some work with Krista also. I've been obsessing about how mantle convection generates plate tectonics. And these are surface predictions of the sort of divergence and viscosity and plate motions from global convection computations. And we know that spreading centers are offset by transform faults, and our models do this sort of thing, but in a very transient way. And the answer is somehow in the rheology of plate boundaries, and I've started to work with folks in Canada. Julie Lohman gave a seminar here who've done similar models, and we can't quite figure out why they give different answers, but it's trying to sort of understand in these oceanic plate only models, what do plate boundaries look like? Next slide, please. And so on the more applied side, I'm trying to not just talk about any general planet, but our planet. We've done a bunch of work to do with the evolution of mantle structure and the links to tectonics and dynamic topography. So recently we had a paper out that was led by Ivan Stroma, who was a Jackson School Plates 40 scholar, thinking about the closure of the Tethyan Ocean over the last, 60 million years ago, and trying to understand how the evolution of land masses and topography affected the exosphere in the sense of closing the seaway. What did that do to oceanic circulation? What did that do to climate? And then also, how did the land bridge evolve with the contribution of a plume? And our case in this review paper recently is that this land bridge that formed around 15 MA and led to the spread of animals was partially supported by mantle plume. I have an incoming student with Julia Clark. We're trying to bring this sort of evolutionary dynamics, mantle dynamics thing together. Next slide, please. And so, big part of that is, if you're trying to understand how much the mantle is pushing things up and down, is seismic imaging. I've gotten over the years into seismology, both isotropic and anisotropic imaging, with a desire to understand the range of predictions we can get. We had a recent paper where we make the case, work by Jill Lenoir and Steve Grand, his group, using full waveform imaging, that we can get a better model of North America. In particular, we're seeing these drippy things, and we're making the case that we're seeing lithospheric sort of recycling in progress. And that, I think, we can validate to some extent with looking at GPS verticals, which are shown here for North America from earlier work by Nicolau and others, with the GA correction. That brings me to my interest in GA, where if we want to say, well, how much of this down and up is due to the seismic cycle, and Cascadia is due to mantle flow, is due to GA, you kind of have to do it yourself. And so that's what Kaixuan is going to talk about at the end here. And what this shows is, well, here's a mantle flow prediction. Some of those features appear to match. One of the places that appears to be going up because of a mantle support is Florida for some reason. And then there's other stuff where we're trying to tease out the signals, right? And it's not sort of trivial to do that. And I think that's it. Yeah, okay. So then sort of moving to the shorter term structure, what my former students in Montreal did is use information from geodesy now, not the long-term deformation, but the seismic cycle deformation, to say something about structure in the Earth. And so this is Tokaoki co-seismic. We've said, well, solve for the slip distribution, but now allow for 3D variations in shear modulus. never been done before. It's kind of fun, and you can complement this with seismic information. What you see is the slab is strong, but then you also see the arc. And for events like Tokaoki, those are, important probes of the Earth. And we've previously done some viscoelastic modeling of the post-seismic part, and we inferred that the viscosity of the mantle wedge and the bending plate have certain features that are consistent with the stuff we do for long-term geodynamics. And so I'm also interested in new ways of imaging the Earth. And I'm going to hand it over to Dunyu, who's going to talk about our efforts to move from a static inversion for structure to a dynamic inversion for the time evolution and the 3D variations in viscosity.
Hi, I'm Dunyu. So I study earthquake dynamics and also a helping hand in Thorsten's group, and I'm honored to work on diverse topics in the last couple of years with Thorsten. And continue on his last slide, and we try to move Simoni's method to viscoelastic deformation. So we involve time in the process. And yeah, the left side is the Thorsten last slide. And first, we need to, so this is a new numerical method. Simoni developed the viscoelastic formulation. And with Phoenix, it's an open source finite platform. And we first need to verify, the method works, right, with other solutions. And first, we try to simulate a 2D subduction earthquake and compare the surface deformation to some other kind of analytical solutions and to see, whether implementation is right. And here is so we have a really thin layer crust, and on top, sitting on top of a really huge viscoelastic half space. And if we zoom in, we have a subducting fault, 30 degrees, and top is elastic layer and viscoelastic layer in bottom. And we try to put some slip on the fault and to see the surface deformation. And this figure shows at 3 time steps over 2 characteristic time scale of viscosity. And we compare the Phoenix solution to a semi-analytical solution. And it may not be easy to see, but we have a pretty good agreement. So it gave us the foundation to move on forward. And later on, we try to apply it to the 3D Tohoku-Oki earthquake model. And then we try to develop the mathematical formulations for the forward and the inverse framework. So although this one looks simple, it actually took a really long time to rule out all the bugs. Next slide, please. And then I will talk another project. It's a new adventure for us to apply AI in earthquake dynamics. So this type of AI architecture is called graph neural network. And it has been quite successful in the last couple of years and to apply to simulate many physical systems. Like here are some examples, like this is the flag, deform under wind, and this is a solid plate and you deform it. And also these are fluid field, and also later on there were water drops, sand, some granular materials. So graphic neural network has been shown really good at learning and predicting physical and even non-physical systems. And here we try to see whether, the question is, can GNN, the graph neural network, can learn and predict the nonlinear dynamics of earthquake ruptures. And here is the typical earthquake rupture simulation. This is the earthquake fault, and we have sleeve, that's the relative displacement between the 2 walls of the solids. And this is the color, and the contours are how the rupture process starts from here and propagate upward and top and the bottom. And could you, yeah, so this is the sleep rate movie of the earthquake process. And we try to train the GNN to learn the process and then predict other stuff. Next slide, please. So The answer is yes. We first built a training data set with 10 earthquakes. The difference is the epicenter locations. And then we train the GNN and test on scenarios with unseen epicenter locations. And so, for example, these are 4 examples of earthquakes in the training set. They have different, epicenter locations. And then we just need the first time step to put in the GNN, and it can predict the next step, and then it auto feed itself to generate a whole sequence of the earthquake dynamics. Could you hover the mouse over the movies? Yeah. So for example, the top is the ground truth. Basically, we use the physics-based simulation software to simulate the process, and then the middle panels are predictions. And you can see the GN learn pretty well how the rupture process. And for example, this is another scenario. And this is the third one. So, and we all use open source software, and like Ecodyna is the physics-based model we have developing, and the GN is developed by UT civil engineering team, and we build on top of that. So yeah, basically the GN can learn, can predict the ruptures from unseen epicenter locations. But we have more stuff on the next slide. So there are 2 advantages, I'll say, with the GN. One is the speed up. So you can see, for example, with 200-meter spatial resolution in the model, and the GN roll out the whole time series in 35 seconds. And if you compare that with the CPU-based, physics-based model, it takes 3,200 seconds. But I should note there is always difficult to compare, the performance of GPU and CPU, because there are different software and hardware architectures. But here we see a really like 90-fold improvement. And if we have higher resolution, we will have more speed up, because the GNN works on a 2D map, it's a fault map, but the physics-based model should need to solve the 3D volume. And the other feature is the strong generalization feature of a GNN. For example, here we train the network on a really small model, like this is the fault dimension in the training set. But actually, you can see the trained GNN can apply to a larger fault. So basically, you can train on small models and predict really large systems, and that's a really amazing feature. Overall, we can save a lot of computations, and basically it will give us opportunity to explore this kind of vast parameter space of these physical systems. And we have other progress going on too, and like currently it can generate heterogeneous stress and even higher model resolutions. So yeah, and there is an ad we submit abstract to AI DT digital twin for Earth system, and you will see there's an ad on TV in the hallway. So it will happen in September hosting. So yeah, hope we can be selected and present the work. Thank you.
Any questions for Dunyu while the next person gets set up? I don't know who's next.
I'm next.
There'll be time for questions at the end also, so.
Okay, I'll just sit here then. So hi everyone, I'm Huiwen. I'm a 3rd-year PhD student here, and my work has been focusing on how does fault geometry affect fault interactions through earthquake cycles, and I'll be showing like one of my case studies. So I'm focusing on the Alpine fault in New Zealand. So this is a big strike-slip fault system that's been pretty active over the paleoseismic history. And then people have been like noticing really interesting like things about this fault along strike. So if you look at the first diagram, it shows you in terms of fault geometry, there's this really distinct change in fault dip along the fault. And then this is from almost vertical to around like 50-degree dipping. And then, so the middle panel shows you the seismicity along strike and depth. So there's also this change in the distribution of seismic activities along depths, and this area actually correspond to this part of the fault, and this is also where like the change in dip is observed. And then the third panel shows the paleoseismic records that people collected from the lakes that is positioned along the fault. And then so this, how to read this diagram is so every single horizontal line is a paleo earthquake, and then the yellow color lines shows you partial ruptures that only go through like part of the fall along strike, and then the red color ones are like through going ruptures. And then this black vertical dotted line shows you where the boundary of the partial rupture is, and then so that also corresponds to where this like change in dip is. So like that got me really interested in this project. So like so I was interested in answering how like what combinational fault properties would control this kind of pattern. I've been running rate state friction based 3D earthquake cycle models that's in an elastic half space. So here I'm showing you this really simple case where I have an arbitrary fault and I'm keeping the frictional properties the same, but I'm changing the dipping angle of the fault. So the first row shows you this 10-degree dipping fault, and the second row is a vertical fault. And the blue and the red on these two diagrams shows you the A minus B value, which controls the frictional property, and the rate state friction loss, which are kept the same. And then the middle panel shows you the earthquake cycle. Basically, every single red color strike is a coseismic rupture, and then blue is interseismic. So yeah, and from one end to the other is like the evolution in time. So you can see that for the dipping fault, you have these alternating big and small rupture patterns, while as like when you have a vertical fault, things are more regular and then both in time and space. And then on the right panel is basically like phase space diagrams where like you can better visualize the stability of the system. So if you have a reoccurring loop that's like slightly triangular in shape, this means your system is stable. You have like very regular ruptures, but if you have like 2 or 3 triangles looping through time, then you have these kind of like stable but varying rupture patterns. So yeah, so this is my current stuff. We're trying to like work towards a benchmark effort that is going to be held in New Zealand in August. So hopefully before that we figure out the numerical headaches.
That'd be good.
Yeah.
Cool. Thanks, everyone. Quick 1 or 2 questions, anybody? Okay, you can come back.
Good afternoon, everyone. My name is Chao. I'm postdoc working with Thorsten mainly. So today I want to talk about the joint inversion of sleep and postness ratio of slow sleep events regions using GNSS data. So the idea came from the fact that Thorsten has introduced his student Simone developed like numerical framework to invert the sleep, cosine sleep from instead of like calculating Green's function, you can actually invert the sleep directly from the PDEs, and simultaneously you can also invert the elastic structure, like 3D compliance. So when I thought about that, I thought, you know, slow sleep event, if you only care about the cumulative sleep on the GNSS record, like from the start to the end, regardless how long it takes, can take a year or take a few months to do that. But if you only care about cumulative slip, the problem itself is fundamentally like the cocyclic slip describing those papers. So here I show, this is from one paper from Kang 2019. What they did is they tried to detect the short-term slow sleep events. These could take like a month or a few weeks, but they are short in period. Also, they sleep for a small amount. So what they did is they stacked these small short-term SSEs, and then the stack records look like this. And then they try to ask what is the corresponding slip for this amount of this ground displacement. And this is their inferred slip, and this figure shows the observed displacement in gray and the calculated slip in blue, and this is their residual. So as a testing case, I'm trying to use the same data, but putting into this framework and try to get my own slipping version. And further, I want to test if I can jointly invert the Poisson's ratio at the same time. Why I'm trying to invert the Poisson's ratio? Because Poisson's ratio is particular related to the high fluid pressure, which is indicated at the region of slow slip events, which has been suggested by seismic tomography and the receiver functions. So this is the image at the specific done at Nankai region, Nankai subduction zone, which is going to be my study region. Could do this. Thanks for it. And then we create this finite element mesh. This is Nankai subduction zone. The Philippine sea plate is subducting beneath the Eurasian plate, and we have this mesh. Then you can have a denser mesh size at the fault interface, and then get it coarser to the size, and eventually at the boundary you get even coarser. First of all, we design a checkboard test. First, we design a 0 to 10 centimeter sinusoidal variation in the deep sleep. So we imagine the sleep has two directions. One is along the strike direction of the fault. One is along deep direction, and we don't assume there's an opening of the fault. So this is a true slip I designed, and this is a predicted slip by the sleep inversion. Note here we assume the entire volume is half surface elastic, has you assume a Poisson's ratio, you assume a shear modulus, and this is the observed slip vector and the predicted slip vector. And you can see the residual is pretty small. So this tells us that with around 40 stations, you are able to see some structure that have a wavelength of 40 kilometers or so. Pretty good. Next slide. And then based on this forward modeling, we went ahead and do the slip inversion, pure slip inversion, using a homogeneous half space. So this slip result is inverted by Carlo 2019. This is our result. So in this figure, these red dots are the locations of low frequency earthquakes. It has been suggested that these locations should be correlated in space and possibly time with the slow sleep, the high sleep region from the slow sleep event. So here, I'm trying to plot the same, but you didn't have the data. So I obtained these locations from a JMA catalog. And you can see both results are kind of similar. We both see the high density region and the low frequency earthquake location track the slow sleep, the high sleep region of slow sleep events. And again, then we can see how our prediction of this ground displacement according to the slip match the observed data. This row, top row is their observation, and the bottom row is our result. And then quantitatively, we plot the histogram of the residual. Blue is our study here. Red is the original paper. It's interesting that our residuals are actually slightly smaller than theirs, more concentrated than around 0. And then we went ahead to explore the possibility of a joint inversion. Here on the left, this is the paper from Charles and Laurel in 2015. They actually had two papers. This earlier paper talks about when you have ground stations without offshore, let's say you don't have a lot of offshore stations and your station coverage is slightly worse, And they talked a few cases that deep or shallow SSE, how the heterogeneity in the structure could affect your inverted slip, and how sensitive your ground displacement would to the change in your structure. So it turns out that for the deep slow slip events, heterogeneity can result in up to 20% of the difference in the slip. And changes in the ground displacement, if you account for the heterogeneity, is above your location error. Let's say your location is, ground displacement is on the centimeter and your location error is 1 millimeter. So you're able to see that variation if the ground is actually heterogeneous. And then we try to do some synthetic tests as well. So for the same, we assume the previous inverted slip distribution is our ground truth. Then we can obtain, their displacement, and we try to add an anomaly layer that is 15 kilometers thick, 5 kilometers above the slab, between 30 to 40 kilometer depth, and this depth is actually known to be, the occurring region of slow slip events, low frequency earthquakes, tremor, stuff like that. And we try to add 50% of this. I don't know why it's not shown, but this is adding 50% increase of Poisson's ratio. And when we try to predict how much the displacement would change. So this is black and blue, and changes small. So I plot the difference in blue shown here. And this is the histogram of that. And moreover, I add a 50% of shear modulus to see how the ground displacement will change. You see that 50% change in shear modulus has a larger effect than the Poisson's ratio. However, the current test shows that the change is smaller than 1 millimeter. So we have to do something. For example, change the shape of this anomaly layer to be more realistic. As the previous image showed, the size imaging probably gives like more wedge-like anomaly and larger in volume than my current model. And I think we can also try to stack different SSEs. If you think the structure does not vary in a short period of time, then you may have a larger change in displacement. And then you can invert the structure. So that's all.
Any quick questions for Chao?
Well, I have a question.
Yeah.
So you have done the synthetic test, the checkpoint test for the sleep, the inverted for the sleep.
Yeah.
And I was wondering, since you do the joint inversion and you do the checkpoint test for
Not yet. Yeah, not the Poisson's ratio.
Yeah, Poisson ratio. Yeah.
I think that would be even tougher.
Oh, okay.
Like now we are assuming the whole a uniform change in volume, and the signal is small. So I'm not very confident about the checkpoint test.
Do you agree with the Williams and Wallace or not?
I think so their displacement, their SSE is larger than mine, and their heterogeneity is more complicated than my simple case. So,
But it goes in the same direction
I think so.
in terms of the patterns.
What do you mean by the variation, the direction of variation?
Yeah.
I mean, it's all over like different directions. It's not uniform, right?
That's totally okay.
Yeah, hi everyone, I'm Chuanming, a postdoc working with Thorsten Becker. I mainly use the seismic imaging, focusing on the seismic anisotropy as a tool to investigate the subsurface dynamic processes. And here shows our result, focusing on the focal plate and trying to use the seismic anisotropy to investigate the oceanic plate dynamics. And the background over here is, so based on the global size surface wave, exponential anisotropy tomography, and we have such kind of fast orientations shown as the blue bars. And so we can use this seismic anisotropy information to investigate. The pedal for over here, compare that with the pedal spinning direction. And blue color means we are consistent with the pedal spinning direction, and the surface wave exponential anisotropy in the oceanic lithosphere. And also we can use the seismic anisotropy from surface wave to give us more insights about the mantle flow directions in the asthenosphere. And so for the Huiwen plate over here, the blue squares over here represent about 250 ocean bottom seismometers. And over here, and also we have a lot of bunches of the onshore broadband stations. And based on such a nice seismometer distributions, and which gives us the confidence to retrieve the azimuthal and structural patterns in the oceanic, such a young oceanic plate, the Huiwen plate. Next slide, please. And so, based on the ocean bottom seismometers records, and previous seismologists has done such kind of the seismic anisotropy studies in the same region and using the PN and SKS and the teleseismic surface wave. And over here shows a previous study by the Huiwen and the Dunyu, and they generate such kind of three-layer model and trying to explain the seismic anisotropy pattern in such a young oceanic plate. But the things they found is they have a very different, faster rotations in the first layer of the Huiwen plate, and they find the PN results are not consistent with the teleseismic earthquake-based seismic surface wave azimuthal anisotropy pattern in the Huiwen plate. And over here, and the reason is they just use the teleseismic-based earthquake surface wave and plus the SKS, and they don't use the ambient noise, which can give us a much more short period information and can bring us the shallow oceanic plate information. And so over here, and we use ambient noise for the ocean bottom stations and plus earthquake events, and which gives us a much larger period band for the surface wave. And we construct such kind of a two-layer model, and one model for the oceanic lithosphere, another model for the oceanic asthenosphere. And over here, we compare our result with the PN. And the blue bars represent our result, and the white bars represent our result, and the blue bars over here represents the other faster rotation models from the PN and from the SKS, and the blue means and they're consistent with each other. So in the oceanic plate, and when we compare our result with PN, we found a very nice fitting in both Huiwen plate and Gouda plate. So over here, the ambient noise gives us more shallow information and provide a more consistent result in such a young oceanic plate. And also our result fits very well with the SKF faster rotations in the most of our study regions. And based on these two-layer seismic anisotropy models, and it gives us more information and about the plate tectonics in such a young oceanic plate. So for example, in the first layer, in the oceanic layer, and our expectation is it can record the faster rotations are comparable to the paleo directions, since in the oceanic lithosphere, the seismic anisotropy are more related to the facial anisotropy. And over here, we compare our result with the paleo direction, and we found a very good fitting. And the light yellow color means they are consistent with each other in most of study regions. And also, in the asthenosphere, in most of the geodynamic studies, and people will use the API model, the absolute plate motion model, to represent the mantle flow directions. So over here, and we use the seismic anisotropy to represent the mantle flow directions, and compare with two very popular API models. One is Huiwen 1A model, another is MOVO model. But we found, over here, actually these two kind of absolute plate motion models, they are kind of consistent with each other in most of the global scales, but they have a very significant difference in the Huiwen plate, about 20-degree difference. And our result fits well with the Huiwen 1A model. You can see over here in most of our study region, but not so well with the MOVO model. And the reason is the Huiwen 1A model, they use a much longer time scale to generate the absolute plate motion model in the Huiwen plate, about 3 million years. But for the MOVO model, they use just a 1 million year, much short time scale, and to generate the plate motion directions for the Huiwen plate. So the new Huiwen model in the Huiwen plate, it more represents the mantle flow directions, while the mobile model more represents the current day plate motion directions. And it fits well. I mean, the mobile model fits well with the GPS result. Next slide, please. So by using the seismic anisotropy, and we can study the plate tectonics, and also another very useful, I mean, inside system anisotropy can provide us is it can indicate the crustal deformation styles. And so over here we focus on the Antonio plate, and we know, I mean, the African plate is, and also Arabian plate are pushing northward, and due to the retreat for the subduction over here, and also the collision, between Arabian plate and the Antonio plate, and the whole Antonio plate experienced the transitional deformation in the interior of it, and also this transitional deformation is accommodated by the two large scale structural fault zones, the North Antonio fault and East Antonio fault. Here shows the historical large earthquakes happened along these two large scale structural fault zones. And over here, why study the seismic performance in this region, and we can also to study the crustal deformation or the surface deformation, and we can use the GNSS and INSAR, and we can also use, and we can see the concentration of the deformation along the two large scale structural fault zones. And also we can use the GNS and GPS to study the horizontal velocity for the blocks. And also, but it just gives us the information about the surface deformation. It's hard to know the interior deformation of the crust. And one way is to use the local earthquake, which can provide us the focal mechanisms. And based on the focal mechanisms, we can have some insights about the interior deformation in the crust. But it's not, you can, from this map, you can see they are very limited, and we don't know exactly the whole systematic deformation the stress and strain rate distribution in the interior of the crust. Next, please, thank you. And so over here, and we generate a seismic anisotropy model, and using the seismic stations distributed across the whole Antonio plate, we have a 3-layer model. And over here, and so the first, so it's an ongoing project right now, and so to generate a comprehensive seismic anisotropy model, and we're trying to include as much as more information. So over here, we're trying to compare our seismic anisotropy model and with the SKS in the 3rd layer in the asthenosphere, and the blue color means they're consistent with each other. And you can see, and this small dense measurements are from the North Antonio fault over here, and we can see they are consistent with each other in the most of the study region. And also in the crust layer, and the receive function can bring us the information about the fast rotations of the tectonic fabrics. But the resolution for the receive function is very limited. So, but for the surface wave, it has very nice distribution and the more homogeneous resolution around the 200 kilometers. So here, but we still can find some coherence with the surface wave-based seismic anisotropy model and the receive function azimuthal anisotropy measurements in the crust. And so over here shows our crust layer, the seismic anisotropy azimuthal anisotropy result in the crust layer. And we compare that the crust rotations with the extensional directions, and from the inverted strain rate measurements from GNSS and INSAR. And blue color indicates they're consistent with each other, and we can see very nice coherence with our fast rotations from the seismic anisotropy and from the strain, from the geodetic measurements. And over two large scale structural fault zone, and which mainly means can be explained by the delocalization of the sand fault deformation in the lower crust. And over here, that's all the things. Do I have another slide? Okay, that's all the things I want to talk today. Yeah. Any questions?
Thank you for coming.
Nice talk. So, I'm wondering, how did you measure the anisotropy based on the 3D wave velocity model? Are you assuming that the wave velocity is fixed, or are you perturbing both the VTMVS and the anisotropy simultaneously?
Yeah, so it's a very classic question, and I know. I mean, there are two kind of flavors. One is kind of, you don't resolve such kind of the relationship between the heterogeneity and anisotropy, and directly, we work for the two parts together. And over here, we kind of using the direct measurements by doing the electron tomography, and we try to decompose the anisotropy part and the anisotropic part in the measurements processing rather than the inversion part. So over here, we can get the anisotropic measurements directly from, the surface with phase velocity information. So, and in the inversion part, they are separated.
Okay, I'll add later.
Who's up next?
And use your computer. Hi everyone. My name is Xiang, and I'm a first year PhD student in Thorsten group to do just why my title is like this. I'm not sure what happened, but I'm here. And okay. So I want to talk about what I'm doing recently. I am using a numerical model to investigate the single and double subduction systems in Philippine Sea. As you can see, there's a plate reconstruction from Kaixuan 2017 back to the 20 million years. And we noticed something that before the 10 million years, there is only one single subduction, not one single subduction, just along this plate boundary, there's one subduction here. But after 10 million years, there's another subduction initiated around this. This is the Dunyu trench, and this is the Philippine trench. So now at present, now it's a double subduction system. And we noticed something interesting that before this double subduction system, like before 10 million years ago, there's a trench motion is in retreating phase. But after this initiated, the trench motion becomes advancing. So here's a 2D model from this article to investigate whether or not the double subduction can do the trench retreating to advancing this transformation. And you can see before 10 million years, there's only one single subduction. And you can see this is the surface velocity of the plate. And if this is negative, which means toward this direction. If it is positive, it's towards this direction. Since the subduction direction is towards the left, so you can see the overriding plate is the velocity is positive. So now this is in a retreating phase, the trench motion. But after 10 million years, they initiate a double subduction just in front of this one. And you can see this overriding plate is in a advancing phase, which means the velocity is negative, is towards left. So they use a simple 2D models to prove this. Also, there are other things happening around the world, not around 10 million years. That's critical time point. And one thing is the Pacific dynamics changes. Around 10 million years, there's a Olapole wandering very fast around just after 10 million years around this. You can see the velocity, there's a peak here. And another thing is the rifting, the faster rifting of Gulf of California just after 10 million years. And here the color, you can see the blue one is orthogonal rifting, and the size of the circles means the amplitude of how strong the rifting is. So you can see those small dots, and blue one is orthogonal, very weak rifting, but after 10 million years, around 5 million years, the very strong strike slip motion with very large magnitude. So they happen just around 10 million years, but we don't know what drives this. And one assumption I got from Thorsten and their discussion is that maybe the double subduction initiation around the Philippine Sea might affect the dynamics of both of them. And so we want to explore whether or not this is a factor to affect those dynamics, or to what extent they contribute to those kind of change. And here I use numerical models by mainly follows the setting from Goldberger Holt 2024 and use finite element code aspects. So first we implement the temperature structure. We convert a tomography model like SME or other tomography models by using a scaling factor to temperature at the mantle temperature structure. And then we implement the slabs by using the slab 2 model, which is constrained by the seismic data beneath zones to constrain where the slab is and the depths. And also about the lithosphere thickness, we use a tomography derived the lithosphere thickness from Steinberger 2018. Of course, we need a viscosity structure. But first, we need a radial viscosity variation. It should be a 2 layers one, which is already proved by try to get the correct GLA and other GIA constraints. We already proved that it should be like 2 layers one, which is a stronger lower mantle and a weaker upper mantle. Actually, we need a very strong lithosphere, but since we already implement the lateral viscosity variation, which is implemented by using a composite rheology dislocation diffusion group. So since the lithosphere we already include in the model, and the lithosphere quite cold than other ambient mantles, so the viscosity is still is pretty strong. And also we can do other modifications if we need. And here is our model's result. Oh, we tested 2 models. One has a double subduction system, another one only has single subduction system, which means the double one, we have both the dashed yellow line and the red line subduction zones. But for the single subduction, we clip the dashed yellow subduction zone. And we compute we shoot our surface velocity here, and the left hand side is the Philippine seas. The blue vector is a double subduction system surface velocity, and the red one is single subduction. You can see there's a sum like the magnitude, and the ambient color here is the magnitude difference between the double subduction and single subduction. You can see the red one here, which means the double subduction gives us a very fast velocity. And you can see from the vector that it shifts around 90-degree direction towards north towards Eurasia. So the double subduction can affect the Philippine seas velocity quite a lot. But if you see it globally, the effect is quite regional. So it's already around the Philippine Sea, and we cannot see like whether or not it changes the Pacific dynamics or the Gulf of California. It's the difference just pretty small. And then we want to again prove that the double subduction system, whether or not it causes a trench advancing, as we said before. And here is just I pull back my first slides to show the previous study. They use a truly model to show that the double subduction system can cause the trench advancing, single one means the retreat. And I also proved this in my 3 global models that the double subduction system, indeed, they try to transform the trench motion from the retreating to advancing. So we proved that also in 3D models again. And then we look at the stress difference. The stress difference is also the difference between the double and the single subduction system. And the blue one means has more extension, and the red one means has more compression. You can see those strong effects around the Philippine Sea, but other places, especially the Gulf of California, the difference is quite small, which means the double subduction system might not affect the rifting of Gulf of California too much in my model. Yeah. And then we did another test. We want to see whether or not the rheological choice, like the non-Newtonian model and the Newtonian model, like you use a power law like 3 or 5, or you use Newtonian model like the only difference depends on the temperatures and the stress dependence is power 1. So it's in Newtonian, and the difference is here. First, the pattern of the stress of the magnitude difference is similar, but the magnitude difference is much larger in the non-Newtonian one because it depends more on the stress, and the stress difference is quite large. But you can see other regions, the difference is quite small, and the velocity, magnitude, and direction also pretty similar. So it's only affected, it's also a regional effect. And also we see the stress one, they just have the similar patterns, maybe, but different magnitude, you can see here. Oh, sorry. So this is what I did now, but I can see more works need to be done, like investigate the tomography effect and other things. And also, those double subduction system initiated like 5 million years ago. The plate boundaries and those plates are in different places. They are not in the current plate boundaries surroundings. So, but I just use a simple model, use current plate boundaries. So it might be a fact. And also, more things need to be tested. That's all. Any question?
Quick question?
So I'm wondering if the double subduction has an impact on the stopping of the retreat and change of the direction of the Isoboning and Mariana Trench.
Mariana Trench, yes, they have.
They have.
Yeah.
Okay. So to what extent?
I don't have such a quantitatively testing it, but it has a transformation from the retreating to advancing in the Philippines.
Okay.
All right.
When you take out the second slide, do you leave the plate boundary in?
No plate boundary.
All right. Sure.
Thank you.
Okay, we're very close to the end of the discussion hour, so I will try to finish in short 5 minutes. So my work is mostly focused on to estimate the impact of 3D viscosity variations and non-Newtonian rheology or GIA modeling. So as all we know, our Earth mantle our Earth mantle behaves as viscous fluid at very long-term time scales, like in mantle convection modeling. And during the intermediate time scales, like the late Pleistocene and Holocene, so the mantle can be treated as a viscoelastic solid. So this means the mantle will has a delayed response to any surface forcing from ice change. So this is good and not good. So good thing is the mantle has memory of the past ice change, so we can measure the outgoing observation of this uplift, for example, around the Hudson Bay to learn about the past ice change, like what the ICG ice thickness models can be reconstructed in this way. We can also just use those kind of signal to learn more about the Earth model, like viscosity in the interior of the mantle. Like the viscosity of the mantle is really the key factor to control this transient process in this surface loading process. And the bad thing is for the people we want to learn more about the current state of the Earth, we have to remove this kind of signal because this will contaminate the current temporary signal. For example, what Thorsten interested in to extract the dynamic tomography from GPS measurements, we have to get rid of this GIA signal. So my work is to test 2 different facts for the GI model. One is we just want to learn how we introduce the lateral viscosity variations in GI modeling and how this model can departure from the 1D viscosity GIA modeling, because most of the GIA groups, so they still use this kind of this 1D viscosity to model this lead motion. So here I gave an example what we want to do here. We just introduce this three lateral variations in lithosphere thickness, also the upper and lower mantle viscosity. And we can see this is from the 3D viscosity, and I also gave a 1D viscosity. We try our best to add more layers to just trace those kind of the lateral average from this 3D viscosity. And you can see, even though I use already 3 layers, I can add more, but I think even though we can add 3 layers, the difference between 3D and 1D it's very large. Yeah, for the horizontal motion, you can say they just change the direction from 3D to 1D. And I compare one of the most classic GI model. They really use 2 layers mantle viscosity, like this green curve gives up mantle have 1 viscosity, one volume viscosity, and then just increase around 10 factor of the viscosity to the lower mantle. And this model, so if you just decrease from 7 layer to 3 layer, you can see the horizontal motion, the directions almost change. So this tells us if we want to remove the GI induced, especially the horizontal motion from other like GPS observations, we need to just have more details about those kind of shadow of the upper mantle in the casings. And besides this variation in the lateral variation in viscosity, we also consider the non-Newtonian rheology. So here I gave an example when we introduced this non-Newtonian rheology, this factor I introduced can affect those effective viscosity. And this left is the non-Newtonian one, and all of those are the Newtonian rheology, which I just use different parameters for the stress, like background stress, the tectonic stress, 3D or 1D, also the transition stress. So we can say overall between the Newtonian and the non-Newtonian and non-Newtonian, we can say for non-Newtonian model, all of those vertical and vertical velocity, they just decrease dramatically. And we look deeper into this this velocity profile, and we can see this non-Newtonian this factor we introduced to this reference viscosity, they just decrease the whole upper mantle viscosity as large as 2 orders of magnitude. So this means the signal caused by this ice change in the late Pleistocene, they almost relax at the present day. So the left signal for the for the vertical and horizontal motion is much less than this 1D, much less than this Newtonian model. And then we have this model predictions, and we just want to compare those with some data. And this is, I show one of the model data comparison we can do is we can just plot those relative sea level curve from the GI model and just compare with data. And this, I gave just some example. They have thousands of this size, but I show some typical size around here, like the Hudson Bay. So this give us a decay. So data tells us a decay, exponential decay through present day. Also the peripheral bulge, so they have a complicated just increase and then just stay there. Also three sites at Antarctica. So for more than ice melting. So compare with those data and model. And we can say those can tell us, okay, in which region we should pay more attention to the lateral variations, and which region maybe we need to consider more about those kind of non-Newtonian rheology. For example, here, so when we compare those green curve, this is from Newtonia, and all of those other curve is from non-Newton rheology, and we can just by able see those non-Newton rheology fit those data, fit those decay curve better. So this may tells us locally, maybe this region, this stress, ice-induced stress may just more like support the non-Newtonian rheology under this sides. But at other sides, you can see the data just take Newtonian rheology better. And in the another round is if you just group, so they just group by linear one and non-linear one. So even if so the dashed line, the difference between dashed line and the solid line is whether I include the lateral variation or not, but they didn't differ much. This may tells us, okay, in this region, the 1D viscosity maybe it's already very good for the prediction. So it's very close to the average of the 3D viscosity is very close to the locally region average. But in the Antarctica science, we can see those model predictions group by either 1D or 3D. So the nonlinear rheology, they're almost identical to each other. So this means whether I include or not include the nonlinear rheology, they will not change much the predictions. This means this maybe means the background stress in this region is larger, but the ice-induced stress cannot surpass this transition stress, so still linear. So even though I just include this nonlinear rheology, but the model, they just pick up the linear component. But the 1D global 1D viscosity, we all know at Antarctica is not precise to capture those kind of Antarctica, even though the East Antarctica viscosity structure, like a very thinner lithosphere thickness, also very weaker upper mantle viscosity. So you can say the 1D and the 3D, they just differ much. And next step, we will just try to compare those with your GPS data to constrain the horizontal motion, especially the vertical and horizontal motion. So to give kind of best estimated GI model for corrections for the other applications.
Thanks, everybody.